The flow of heat can be made to do work and vice versa. We're talking about work and we're talking about energy and we're talking about heat today. And what is energy? Well, we've talked a lot about kinetic energy. We've talked a lot about balls colliding together. No more balls colliding together. And it might seem like kinetic energy is the king of all the different types of energy, but we will unseat kinetic energy today. First, jumping off a springboard. Lots of different types of energy conversions here. We'll start with the diver in this position, and as you can see, she's off the ground, so she's got some gravitational potential energy. Also, if you look at that springboard, it is bent. It's like a spring potential energy. Up in the air, we are at a max height here. Ignoring the horizontal velocity, we'll say that she has nothing but gravitational potential energy at this point, and just for an instant she's at rest in the vertical direction, and then she starts moving downwards, and as she moves downwards she's converting that gravitational potential energy into kinetic energy, going faster and faster. Soon all her energy is kinetic energy, and then splash, she's underwater. And she slows down, of course, before she hits the bottom of the pool, we hope, and that's because work is done. Work is equal to the change in energy. Where did her kinetic energy go? Work of friction, work done by friction, friction between herself and the water. We have a downward displacement, an upward friction force, and it robs her of her kinetic energy, just like in the last video. We had the friction force destroying the kinetic energy of the car. The friction force, and that means thermal energy. Rub your hands together, and you'll feel them start to warm up. The same thing's true with the water that stops the diver from hitting the bottom. And we're not talking exactly about thermal energy, though. We're talking about the flow of heat, which can be made to do work. And what's the difference between heat and temperature and thermal energy? Well, that's a real key difference for us, and we'll get to that in just a second. First of all, what do we mean by the flow of heat can be made to do work? The flow of heat, well, heat is an invisible fluid. We're treating heat like an invisible fluid, just like water is an invisible fluid. As this water runs over this water wheel, it does work. The flow of water over the wheel turns the wheel and can grind flour. It can do all sorts of work. Or if you don't have a stream nearby, you can use coal and a steam engine. Same sort of thing here. Think about it not in terms of engineering, just think about it in terms of energy transformation. The gravitational potential energy of the water being converted to useful mechanical energy, or how about the chemical energy of the coal being converted to that spinning wheel there in the Industrial Revolution. But a steam engine will get you only so far. How about a diesel engine? The same sort of thing, the same sort of energy transformation. And I'm telling you, whether you talk about a water wheel, a steam engine, or a diesel engine, heat is kind of an important thing to worry about. And here we have an electric heater, which seems like a lot less complicated than a diesel engine. And the reason it seems that way is because it is a lot less complicated than a diesel engine. But all three of our engines did create some sort of heat. You're talking about the exhaust of the diesel engine, or you could be talking about the friction in the water wheel. Anyway, this is a heat engine. This is how we are idealizing energy. We have energy coming in from the hot reservoir at temperature T hot. Energy, waste energy, exhaust energy being exhausted into the cold reservoir at Tc. And as heat flows from the hot reservoir to the cold reservoir, some heat can be turned into useful work. So what is that hot reservoir? Well, that's a tough question. You can think about it as the chemical energy of the coal or the chemical energy of the gasoline. We'll do more on this in the next chapter as well. But since we have an input and an output here, we could talk about the efficiency. The efficiency, what you get out divided by what you put in. The work out divided by the QH. There's always going to be less than 100% efficiency. There's always going to be some exhausted heat. That's what we're talking about. Some exhausted heat from the diesel engine, some wasted heat from the steam pump, some friction in the water wheel. So that's where we're going. Here's where we're starting. The flow of heat can be made to do work and vice versa. But what is heat, and how is it different than temperature and thermal energy? Well, consider a beaker and a bucket, and there are the temperatures. So you can see that the small beaker has a higher temperature. The larger bucket has a lower temperature. That's clear enough. 100 degrees C is a greater temperature than 60 degrees C. But we can also, because the bucket is bigger, we can say that the bucket has more thermal energy, less thermal energy per molecule. It's a way to think about temperature. Less thermal energy per molecule for the bucket, but a lot more molecules, a lot more overall energy. The question is, which of these containers contains more heat? That's the question, and that is a bad question. You cannot answer that question. You cannot contain heat, and I'll tell you why. Consider a paperclip. You toss the paperclip into, or two paperclips in, one into each of these containers here, and ask the paperclip. Remember the talking paperclip from Windows 95? Ask the paperclip, who gives you more heat? And the paperclip will tell you that the paperclip gained more heat from the beaker and it gained less heat from the bucket. Heat is the energy transfer due to a temperature difference. Ask the paperclip. Think of the paperclip, or forget the paperclip and think about a swimming pool. Different situation here. Now we're going to toss the liquid from the beaker into the swimming pool and toss the liquid from the bucket into the swimming pool and ask the swimming pool which of these containers gave you more heat. Heat is the energy transferred due to a temperature difference, and the swimming pool disagrees with the paperclip. The swimming pool says it gets more heat from the bucket, which had, we remember, overall more internal energy. And internal thermal energy is kind of hard to understand when we're talking about a liquid. There's a tension in these next couple chapters between talking about liquids and solids and talking about gases and their kinetic energy. This is the kinetic energy of heat. There are other theories of heat. We're talking about the kinetic energy of heat, which is easiest to see if you're talking about gases. All those gas molecules, those ideal gas molecules bouncing around, elastic collisions with one another. Remember, elastic collisions that do not lose any kinetic energy. Elastic collisions with the container walls, that's where pressure comes from. And an equation for thermal energy. Thermal energy is equal to 3/2 NkBT. N, capital N, is the number of molecules, Kb is Boltzmann's constant, and T is temperature. Temperature measured on the Kelvin scale. The Kelvin scale, a good ratio scale. A ratio scale meaning that it has a meaningful 0.0 Kelvin. What does 0 Kelvin mean? It means no thermal energy. We were talking about thermal energy for a liquid a second ago. Now we're talking about thermal energy for a gas. No thermal energy for a gas when there is no motion at all for these gas molecules, when they are all tired and napping and not moving at all. Speaking about moving at all, we could add up 1/2 mv squared, the kinetic energy of all those particles. We could add them up and equate these equations and get this, an equation for the root mean square velocity. The equation for the root, what is the root mean square? It's the square root of the average of the squares. Not a crucial detail. But this is some measure of how fast those molecules are moving. The key thing to know, though, is that they are not moving all at the same speed. It's kind of like a mosh pit, with some particles moving slower and some moving faster and most moving at an intermediate speed. It is like a mosh pit, but more precisely it is the Maxwell-Boltzmann speed distribution. Like I said, just a couple molecules moving really slow, just a couple molecules moving really, really fast. Most of everybody is moving at an intermediate speed, and the root mean square velocity gives you some idea. It's not exactly the same as the most probable speed or the top of this speed distribution hump here, but it's near there, a little bit to the right. Again, this is the speed distribution for a sample of gas. Not all particles are moving at the same rate, and consider two samples of gas. Here we'll say it's the same type of gas, but one sample is hotter and the other sample is cooler. Notice here that the hotter gas has overall a greater speed, and this is a speed graph. You might be thinking, well, shouldn't you be talking about velocity? Well, if you're talking about velocity, you'd have to worry about direction, and we have the same number of particles moving to the left and to the right, so technically speaking, the average velocity of the gas molecules is 0. In this case, it makes more sense to talk about speed, or consider two samples of gas both at the same temperature but different molecules. The lighter molecules would be moving overall faster. A sample of hydrogen gas at 20 degrees C would have a higher average velocity than a sample of oxygen gas at the same temperature. The Maxwell-Boltzmann speed distribution, and there it is, and it's pretty ugly, but there it is. But hey, these are some of the same quantities: mass, temperature in Kelvin, of course, K, the Boltzmann constant, some of the same quantities we had in our shorter equations. So yeah, we're not using the longest equations we possibly could. And we have here a sample of gas bouncing around, and we're thinking about its energy. Heat is energy transferred due to a temperature difference. And if you're thinking about energy, let's talk about energy conservation, and let's call it the first law of thermodynamics. The total change in the energy of a system is equal to the work done on the system, the work and heat put in, minus the work done by the system, the work and heat taken out, which is probably the worst definition I've ever written or ever copied down. What I'm trying to say here is that there are two different ways to raise the thermal energy and the temperature of a glass of water. We're talking about water now. What happened to gas? We'll get back to gas in a second. Number one, in order to raise the temperature of the glass of water, you could, everybody wait for this, heat it. You could add a delta Q. Q is heat, energy transfer due to a temperature difference. Convection, conduction, or radiation, all good, three good ways of adding heat, or flame here, adding heat to that sample of water. Or you could stir it. This is a real life physicist with a blender. He is taking the temperature of the water, blending it, and then taking the temperature again. And you'll have to take our word for it here, but you could repeat this yourself. The temperature of the water increases, which it turns out is a historically significant experiment done by James Joule. This is work being done on the water. It's speeding up the water. You hit it around with those blades and you're speeding up the water molecules back to a gas. How can you do work on a gas molecule? You can compress it. Here we have a cylinder. We are compressing this gas. We are doing work. Force times distance, a compression force, a compression delta X, positive work being done on the gas. The gas gains energy and warms up. Here is a bike pump. This is another video. This guy is using the bike pump. This guy is finding out that the bike pump, have you ever pumped up a bicycle and then felt it gets warm? Because E thermal is equal to delta W plus delta Q. Now this is a crazy statement here, but the bike pump warms up even though you don't heat it. You're not heating. There's no convection, conduction, or radiation happening. Sounds strange to say. But the bike pump warms up, the gas inside it warms up even though it is not being heated. Work is being done on it. Just like the blender isn't a heater, the blender is a blender. The opposite is also true. If the gas expands, it is doing work against the environment. Here the compression force is down and the delta Y, I guess you could say, is up. Force and displacement in opposite directions, just like the diver. We have negative work done. The gas loses energy and cools. The force from the atmosphere is still pushing down, even though the gas is expanding and pushing up. The gas loses energy and cools just like this compressor. It's blowing compressed air out, and as the gas is at room temperature, and as the gas expands, it cools. As gas expands, it wants to cool. Two consequences of the first law of thermodynamics, and because those were so good, we'll have a second law of thermodynamics, which says that entropy increases. The total entropy, or disordered energy in a closed system, will always tend to increase over time. It'll always tend. What does that mean? That's a crazy law of physics. To always tend to do something, turns out it's partially statistical. There is so much more to say about the second law of thermodynamics. There are 3 videos on this channel about the second law of thermodynamics that goes into way more detail than anyone needs to know for the final exam in this course, but they're there if they're there. But what we're saying here, one consequence is, with entropy, disordered energy increases. One consequence is there is a maximum possible efficiency to any heat engine. A maximum possible efficiency, whether you're talking about a diesel engine with some exhaust heat, a steam engine with some wasted heat, or even a water wheel with some work lost due to friction. There's some friction as the thing spins around. There is a maximum possible efficiency greater than which you cannot get. Back to our idealized heat engine again. We have energy coming in from the hot reservoir, energy being exhausted into the cold reservoir. Speaking of exhausted, some work being drawn out, some useful work being used from that engine. Or you could flip it around and talk about a refrigerator. Here's a refrigerator or a heat pump. What does a water pump do? A water pump pumps water where it don't want to go. A water pump pumps water from a lower elevation to a higher elevation. You add in work and water goes from a lower elevation to a higher elevation. This refrigerator does the exact same thing. Energy comes in and heat is pumped from the cold reservoir up into the hot reservoir. Your refrigerator goes out. What happens? Hot air seeps into the refrigerator over time and all your food goes bad. It takes energy to pump the water out or pump the heat out in the opposite direction that it wants. And if you're thinking to yourself, I wonder why heat flows naturally from hot to cold, that is also a consequence of the second law of thermodynamics. I'm getting confused here. Let's just go back to this heat engine and we'll consider 3 different heat engines and we'll say whether or not they're possible. Here's our first heat engine. We have a hot reservoir at 600 Kelvin, a cold reservoir at 300 Kelvin. Looks like we are taking 10 joules of energy out of the hot reservoir, using 5 joules to do useful work, and exhausting 10 joules into the cold reservoir. Can't happen. Violates the first law of thermodynamics. Look at that heat engine. It's a fiction. It's a fraud. You're getting 10 joules in and putting 15 joules out. Violates the law of conservation of energy. Can't happen. Here's another heat engine. It looks kind of the same. It's another totally different heat engine. This time 10 joules go in, 6 joules come out as useful work, 4 joules go into the cold reservoir. The first law of thermodynamics is happy. Energy is conserved. 10 joules in, 10 joules out. The second law of thermodynamics, however, what's our efficiency? Our efficiency is, again, efficiency is what you get out divided by what you get in. Efficiency is 60%. 6 joules out of useful work for 10 joules put in. The efficiency here is 60%, and that is not okay. Not okay. Why is it not okay? Because of the temperature of the hot reservoir and the temperature of the cold reservoir. Look back to that maximum possible efficiency equation. Look back to that equation, and if you do the details, you'll find out that 60% efficiency is more than the max possible efficiency. And you're thinking to yourself, well, what if we just get out the grease and grease up the engine and then change the oil? No. If the hot temperature is no hotter than 600 and the exhaust is no colder than 300, you see how having exhaust at absolute zero would be helpful. Anyway, this is the last one. The third heat engine is the first law of thermodynamics. Yep, totally happy. How about the second law of thermodynamics? 40% efficiency in this case. And yep, that is allowed, which makes us super excited and happy. Maybe not that excited and happy, but pretty happy.